So last time we mentioned that you know when you have a lot of molecules that's moving around in space, they're all moving at a different velocities, and we are not really interested in following each molecule's velocity. Instead, we want to know how they behave as an ensemble, which you have to use statistics in order to study to find out the velocity of the like average velocity, the most probable velocity, and also what is the other velocity? The root mean square velocity, right? And we use the Maxwell's distribution velocity distribution law to find out all these quantities. So last time we mentioned that when you have the average velocity, the average velocity would take up the form, and basically the average velocity is equal to what is the expression for average velocity? The average velocity is, let's see, the square root of a times RT and then over pi over m. So this is the average velocity of, let's say, 10 to the 27 of this sort of molecules. So this is the average velocity, and also we mentioned that the v square, this v square of the average. So let's say the velocity square, and you take the average. That is equal to 3RT over n. Okay, so this is v squared, and then you take the average. So now let's say we want to know what is the average kinetic energy of the system. We have a room full of molecules that's flying around. So of course, in order to calculate the average kinetic energy, we will just by using, we just like each individual particle is going to moving at 1/2 mv squared. That's the expression for the kinetic energy, right? So this is individual velocity, and then we want to take the average. So we sum up all the kinetic energy, and we take the average. That will give us the average kinetic energy. So if you look at this expression, we know that 1/2 is just a constant, doesn't change. And the mass of the particle doesn't change as well. So what needs to be averaged would just be your v squared, right? So this is v squared, and you take the average. So what is that expression? V squared, and then take the average. We just mentioned that that would just be 3RT over n, which is the square. If you take the square root of this quantity, that will give you the root mean square value. So in that case, we can just replace this quantity with that expression. So what we have here is a 1/2 little m, which is the mass of each individual particle, and times 3 times the ideal gas gas constant times the temperature, and over the capital M. Now capital M is the molar mass. Okay, so what you have here is that you have 1/2, and then you have your little m here, individual particle, the mass of the particle. You have your 3, you have your r, and you have your t. And I'm going to replace my capital N with this expression. How do we calculate the molar mass? The molar mass will be individual mass times the molecule in 1 mole, which is the Avogadro's number. So in that case, you can see that your m cancelled. So what's left would just be 3/2, and then times RT, and then over the NT. Okay. So what is the gas constant? The Avogadro's number. If you recall, that would just be the Boltzmann constant. So this ratio is just the Boltzmann constant. So what's So really, so the kinetic energy really comes down to a very simple expression, which is 3 half the get the rule. Just hold on. Sorry. That was just 3 halves k, and then let me just unplug my phone, which is the 3 halves, and then gas constant, and then times temperature. Okay, so you can see that the average kinetic energy becomes very simple, very simple expression, which is just 3 halves and then gas constant times the temperature. So what does that mean? What it means is that regardless which molecule you're dealing with, as long as they have the same temperature, then the kinetic energy, the average kinetic energy will always stay the same. And also you only just just give me a second. Shoot. All right. You know, let me stop here. Oops, stop recording.